Hello. I'm just gonna stream like this then. Okay. I'll push that back. Okay. That's my laptop's edge. There we go. All right. Good evening, fancy meat computers. How's everybody today? Hopefully everybody found the lecture. Anybody in the lecture room right now? Apparently in the 1MD3 class, like about 8 of them were actually in the lecture theater anyway. They put the live stream up on the projector screen, so that was fun. I hope to see a picture of that at some point. How is everybody? Silly thing gets twisted. Boy, you're a chatty bunch today. I'm doing all right. Thanks for asking. Just, you know, it's cool having an 11-month-old, but he's definitely a germ factory. So, whenever he picks anything up, the whole house gets it. And, you know, he kind of, like, compulsively puts everything in his mouth, so. So that's how it goes. Okay. Well, I guess we might as well get started then. So, thank you. I hope I get better soon too. I feel like I'm on the other side of it. This morning was the worst. I was like dead to the world. Try a factory reset on him. Oh, well, you know. Yeah, no. Wait till Musk gets us our neural links, then factory reset on the neural link just erases all your memory. Yeah. Perfect. Anyway. So, the last time... Oh, by the way, I finished the slides and I added some memes. So I'm going to just quickly go through the memes because they're kind of funny, I guess. So, here's a meme at the home of the Fourier transform family. I wish Cincy would stop playing with that imaginary friend of his. Don't worry, it's just a phase he's going through. Da-dum-tsh. Here's another one for you. I didn't make any of these, I was too lazy. I just found them on the internet. Electronics nerds are nerds. So, So we were talking about digital to analog conversion technologies now that we've talked about analog to digital at some length. We had started talking about PWM. We had not quite yet gotten to the idea of filtering, what exactly it means. I understand a fair number of you have already done a signals processing course, so for this, you're probably not going to hear anything you haven't heard already, but for those of you who haven't, we're going to go through the rudiments of how one goes about filtering a signal. After that, we're going to talk about the resistor ladder, and then we're going to talk about the resistor string. I've got an exciting new means of circuit analysis that might be new to a few of you in the resistor ladder segment. We'll see how well I can do drawing diagrams over this. I'm very disappointed because I really wanted to do this lecture in person so that I could have the chalkboard. I was planning the slides, and I was like, well, I have a chalkboard now, so I could just do the diagrams on the chalkboard. And it's like, well, best laid plans. We'll muddle through. So let's talk about filtering. So I've alluded to this MS Paint. No, my friend, we use Krita in this classroom. MS Paint. What do you think this is? Do I look like I run Microsoft? I ask you, do I look like I run Microsoft? I don't look like I run Microsoft, no. I certainly don't run it. I don't use it either. Bop, 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 bop. But yeah, get ready for that. Linux Paint. There we go. Yes. So frequencies. It's kind like one of the fundamental sort of ways you need to wrap your brain around signal processing in order to really start to understand how it's useful is you need to start thinking not so much in terms of amplitude, but in terms of frequencies. Often in nature, we are confronted with signals with many different frequency components. So the idea is, in general, you can have an incoming signal that has a large number of different frequency components that have sort of been added together or laminated into a single signal. This is actually quite frequent in nature, and it's a frequent way that information is transmitted. If you think about the human inner ear, it's designed such that different frequency oscillations in the air vibrate different patches of small hairs on the inside of the organ. Thus, humans can distinguish multiple frequencies simultaneously. You can make similar arguments about light, right? The frequency of a the frequency of a photon is perceived by us as being color, right? One might much more usefully derive information optically from the frequencies which are contained in the photonic signal which is entering your eyeballs, rather than the mere amplitude. So this is a very, very fundamental physicsy kind of thing to do. And human beings have several sense organs which are attuned specifically to this type of thing. So, this function of the inner ear and the eyeball is replicated mathematically by the Fourier series. It turns out that so long as a function or signal is periodic, it can be expressed as a Fourier series. A Fourier series is some constant value, added with the sum of the cosine function with a number of different amplitudes applied to it, all with increasing frequency, increasing by n. I sound like a jazz radio station DJ. Smooth jazz. Yeah, when you're in front of a microphone all day, you kind of just get this, nice dulcet tone. Like the Fourier series. Whoa. No, it's Fourier, not Fourier. So, basically, you have two terms here. The sum of a whole bunch of cosines and the sum of a whole bunch of sines, each of them with different frequency components. And you'll notice that we go all the way from n equals 1 to infinity. So, in theory, these things just go on with increasing frequency forever. But, of course, when you're dealing with actual physical reality, you're going to want to cap that. You're going to want to cap the frequencies at some point, right? It doesn't, like, as we explored with the Nyquist theorem, there's only so much frequency you can usefully detect with a certain sampling frequency anyway. So above that, whether or not it contains useful information, that's something for you and the sampling frequency to decide together. So, basically, we can reconstruct any signal by knowing the amplitudes of an infinite series of sinusoids of increasing frequency. So this is interesting, right? The key take-home here is any function, any periodic function, can be expressed this way, right? No matter what it looks like, we can find values of a naught through a at infinity, I suppose, and b1 through infinity that make this an actual exact replication of the original signal. So, basically, we can reconstruct any signal by knowing the amplitudes of an infinite series of sinusoids of increasing frequency. The way you construct a Fourier series from an arbitrary function is via the Fourier transform. The formula for the Fourier transform has been intentionally omitted from these slides so that you don't think I'm going to quiz you on it. I'm not going to quiz you on the Fourier series, on the Fourier transform. What's more important to me is that you pick up this kind of conceptual idea, right? That we can express any signal as a series of sinusoids that have been summed together. So, for example, if we take our well-familiar square wave, right, and we extract out the first 5 sinusoids, which all can be used to reconstruct it, you'll see the first one is quite big, has a fairly large amplitude. The next one is smaller, increased frequency, then smaller, then smaller, then smaller, decreasing the frequency as we go. If you sum all of these things together, you get something that looks reasonably like a square wave. And the more frequency components you add to this, the more closely, the more tightly, this will resemble a square wave. I'm sorry if this has already been mentioned, but what is the test up till? Actually, it hasn't been mentioned yet. The test will cover up to the end of economic stuff, the economic stuff. So this topic 6, digital and analog conversion stuff, that'll be the exam. That will not be the test. Okay? So this Fourier series can only replicate signals if they're periodic. So a non-periodic signal can't be replicated using it. Well, you can. So this is, David, this is kind of the approximation that you would use, right? If you wanted to replicate a non-repeating function, right? What you do is you just identify that segment of it that you're interested in representing as the Fourier series, and then you declare like a start and an end point to that. You pretend that it repeats after that point, and boom, periodic function. Make sense? So yeah, like there are little mathematical ways you can use to get around it. Like if you have a function that just kind of never ever repeats, you know. Yeah. Like for example, a noise signal, you know, like random electronic noise. In theory, that's randomly derived, so no periodic content should be in like a straight noise signal. That being said, we still very usefully perform frequency analysis on it, right? So yeah. Good. Here are a few more examples, just in case you are interested. Are we covering all of topic 4? We still haven't finished the end of interrupts. Yeah, obviously we won't test on the parts of the interrupt slides that we didn't cover. Okay. Oh my gosh. I'm sorry, I have to let the cat out of the room. Give me just 1 second. So, what you get here is the Fourier approximation of a bunch of different signals as we add frequency components. So it's kind of hard to see, but the red line is like right along the x-axis here. And then we proceed in chromatic order. So the orange line includes 1. The yellow line includes 2, then green 3, blue 4, etc. So, anyway, a sawtooth wave, which is a it's a disjoint wave, right? So, it's a piecewise function. So you can see 1, 2, 3, you get the idea. Even somewhat exotic functions like triangle waves and semicircles can be represented this way. Notice in the triangle wave particularly, the closer the approximation we get, the tighter it binds to the triangle, and like the more point we have on the pointy ends. So there you go. Semicircle, of course, you'll notice the red line has been offset from the x-axis, because it's sort of the average signal in this case is above 0. MATLAB flashbacks. Oh yes. So by plotting the amplitude of these frequency components versus the frequencies themselves, we can derive some very useful and interesting information. So for example, the following graphs are frequency versus amplitude for men, women, and children using different speech patterns. So you'll notice that both women and children have like not a whole lot going on in the 125 to 200 hertz range, whereas males fill that out, and you know, if anything, yeah, basically the whole business where men have deeper voices than women on average is illustrated by the sort of these guys being down here and these guys being up here on these different graphs. If we were in class, I would love to demonstrate the graphs audibly. Yeah, I know, right? I'm telling you, I'm really sorry I'm sick today. I wish I was in class, because this would be more fun in class. But yeah, so in general, you'll notice that like a few other things, like when someone is shouting, if that person is female, they sort of are most using frequencies in the 1250 to 1600 range. Males are using them in the 1250 range, but it drops off a little bit more. We've got more in the lower range. And also you can see we shout a little louder when we're shouting. But yeah. So these are the frequencies that people speak at. Well, it's kind of interesting, right? Human speech is an interesting thing because when you speak, you're actually projecting a large number of frequencies all at once. Like you are actually speaking one of these frequency laminated signals. Like if you think about what a sine wave, like you can, like if you go and like go to YouTube and just have it like say play a sine wave for me, you can listen and it's like a single tone. It's like ooh, something like that, right? Something as rich, like the rich texture of human voice is contributed by the fact that there are so many different frequencies that are all going on at once, right? So this is like these. Obviously, you'll use different frequencies when you're using different like phonemes and stuff like that. But but yeah, these are the frequencies that people typically use in the various categories. Incidentally, yeah, and the y-axis here is amplitude. It's yeah, amplitude. So there you go. So a lot of very interesting information can be produced by this type of analysis, which is also sometimes called harmonic analysis. So we emit all these frequencies at a single time. Well, you will emit some frequencies at a given time. So let me just find something interesting. Let me see if I can find something here. Fourier transform of a voice sound. Oh, there we go. I found something. It's kind of like the JPEG is quite crusty, but let's take a look at this, shall we? And this isn't really related, but you know, it's interesting perhaps. So, frequency components of various phonemes accompanying sort of the throat your shape, the shape your throat takes when you make these sounds, right? So it's ah, e, and oo, right? So ah has this breakdown of frequency versus amplitude. E has this one, and oo has that one, right? Now, I think that this actually goes up further than the graph here by a fair amount. Let me just take a look here. No, I think it's fine. So it's 800. This is on a logarithmic scale, by the way. At least it appears to be. So, yeah. Oh, it's actually fine. So yeah, you can kind of just like nestle these guys inside of there. So these are the when you speak, these frequency components are what's in the sound, and that's how your ear picks up an ah sound versus an oo sound, is because the specific areas of your inner ear tuned to 900 hertz activate a lot, 1200 activates a little, and then you have another peak at like 2500. Like your brain picks all of this up and interprets it because that's how brain do, right? So it's really cool, I think. So when I make a sound, there are multiple yeah, good. So anyway, so now that we know that signals are composed of frequencies, we may now make some general observations about those frequencies. So, we are often only interested in frequencies within a specific range. Consider audio signals. Frequencies outside the range of human hearing are not useful to keep inside of audio signals. Right? If it was sufficiently detailed, could we use these frequency/amplitude graphs to digitally recreate sound? Yeah. Yes. Commander Fox Q, I'm about to blow your brain. What do you think that auto-tune is? Auto-tune is just taking that graph, that signal, moving it so that it sounds like it's at the right pitch, right? Because the pitch of the voice is also carried by frequency, right? So all you're doing is you're literally taking someone's voice and like shifting its frequency so that it, like shifting the whole graph up or down so that it sounds like it's at the right frequency, right? So radio waves also make sound, technically. Well, sound waves and radio waves are two different media, right? Radio waves pass through photons, right? Whereas, obviously, audible sound comes through the vibrations of the air, or water if you're underwater, right? It's like sound is transmitted by fluctuating air pressure, whereas in radio it's photons. But yeah, it's like the frequency in the radio transmission would like be translated directly to oscillating pressure in the air, which is what you hear. But yeah, I mean, if we had a sense organ that could detect radio transmissions, then yeah, it would be very similar to how we hear sound. Yeah. Yeah, like science is cool, right? I hope that like you guys have felt like this has been like a science is cool kind of series of lectures. But yeah. So when we filter a signal, we are selecting which frequencies to amplify or make stronger and which to attenuate or to make weaker. This is actually how an audio mixer works. What boosting the bass actually does is it increases the amplitudes of low frequencies and maybe slightly attenuating high frequencies. So, like, basically, like I talked about how with auto-tune, you're taking the whole distribution and you're shifting it up or down. With filtering, you're not shifting it back and forth. You're like you're playing with a multiplicative factor to raise or lower the amplitude in certain areas, right? So you've got lots of different types of filters, right? Low pass, high pass, band stop, low band pass, high pass, low band high pass, etc., etc. So the one that we're going to be talking about most is low pass. But so take these sort of views, right? Think of this as being a function, right? Like a mathematical function that you are multiplying against the Fourier transform, right? The frequency components. So anything that's, and like think about this, like this line here, think of that as 1, although it doesn't need to be. Filters can amplify as well as attenuate. So if this is 1, everything up to about here gets multiplied by 1 and is unaffected by the filter. At this point, the amplitudes of the frequencies start decreasing rapidly until eventually everything past this point is just let go of completely, right? So if you take these functions and multiply them with the Fourier transform of your signal, you will keep only certain frequency regions. This is exactly how audio mixing works. Yeah. So, back to PWM. So PWM signals are essentially square waves. Under harmonic analysis, all of the quote-unquote sharpness of those sharp digital edges is contributed by high-frequency sinusoids. Therefore, applying a low-pass filter smooths out the sharp edges. If you smooth out these sharp edges enough, you will get something reasonably close to the average of the signal. Passive low-pass filters are also very easy to construct. This is how you do it. So you have voltage in on one side, you have a resistor and a capacitor, and then you have the voltage out. This is called an RC circuit, right? It's passive low-pass filter. It's called passive because there's no voltage source here, so it passively filters. So yeah, essentially what happens here is that if you have high frequency oscillation inside of the voltage, the higher the frequency of, like, the high frequency modifications will pass through the capacitor straight to ground rather than out off to the load. So that sort of damps down on, it clamps down on the high frequency stuff and leaving the low frequency stuff. And you can configure like what frequency you keep, like where the cutoff is, right? You can control that by controlling the values of R and C here. But yeah. Any questions about all of that? Give me a thumbs up if you're still listening. Awesome. Cool. Excellent. So that's all I have to say about PWM. Let's move along to the R2R. I want to pronounce the dash as 2, so it would be R22R, but I'm just going to call it R2R. Can't find the thumb. Well, that was enough. That was good enough. Resistor ladder digital to analog conversion. So this one's interesting. It requires a bit of math to figure out why exactly this works, which we're going to get into how to do the mathematical analysis here. So our final two digital to analog circuits, resistor ladder and resistor string, are true many-to-one techniques. So whereas with PWM, we were kind of just spoofing, we were using time instead of multiple pins in order to reconstruct a signal. That's fine, but sometimes you need a precise digital signal at a precise time. Like PWM would not in any way be the correct way to go about producing an audio signal, for instance, right? It's much better suited to like motors and that sort of thing. So we have the following circuit. We're going to work with like 4 pins, just because that's more than enough, right? So we've got 4 pins, VA, VB, VC, and VD. Well, that's the voltages, but we've got pins A, B, C, and D. We have attached to each of those a resistor, which has a resistance of 2R. We have between each of them a resistor of resistance R. And then at the end, we connect that to ground with a resistor that is worth 2R. Right? So this is the least significant bit. This is the most significant bit. So if we sort of think about our intuitions with respect to how much voltage each one of these guys should contribute, the most significant bit should contribute half the voltage. The next one, 1/4. The next one, 1/8, and then 1/16. So you might be able to like kind of get an idea of like this might make intuitive sense to you as a circuit, because it's like, okay, we've got voltage coming in here, half goes this way, half goes that way, right? But we need to perform some actual circuit analysis to verify that this actually works. And it's also a really cool and interesting form of circuit analysis that you may not have seen yet. Well, anyway, we'll get to it. So each one of these pins is configured in push-pull configuration. So obviously, these are going to have to act as voltage sources, right? There's nothing that's going to be accomplished by these things being drains, at least not with a ground connected out here. And Vout is not used to power the rest of the circuit directly. An operational amplifier, not pictured, is used as an active voltage supply matching the output voltage level. So we boost it with an op-amp so that we're not running the circuitry off of this circuit specifically, right? We're just using this to establish the desired voltage level. Make sense? So, in order to see how R2R DAC works, we will need a method of circuit analysis that you may not have seen before, Thevenin Analysis. So I just want to put a poll out there real quick. Have you guys heard of Thevenin Analysis before? Or have you done Thevenin Analysis? You have? Okay. I want the poll though. You guys did it already? Okay. Well, that'll make this go faster then. Oh. Heard of it, don't remember how it works. Well, it might be useful to have a bit of a reminder then anyway. Good. Well, that's interesting, because, like, I remember when I did it, which was a long time ago, to be fair, they didn't actually cover Thevenin analysis. Like, personally, I hadn't even heard of Thevenin analysis until I was making these slides, but covered it a while ago. If the poll was about how much we remember, it might be reversed. Okay, I'll do that one. Clicked no, but it voted yes. Oh, that does sometimes happen, actually. Okay. How many of you could perform? I'm going to ask it. Could you perform Thevenin analysis if your life... Wow, I was going to say if your life depended on it, but there we go. Near the start of the semester. Okay. So Thevenin analysis is extremely useful for digital circuitry. And when I say digital, I mean like the microcontroller type analysis. Okay. So like 3/4 of the class could use this review, it seems. So I feel more justified now in doing it then. So, in the same way that a function in software modularizes a piece of software so that we can deal with it only as it's externally relevant, Thevenin analysis is a similar technique for taking a bunch of circuitry and just kind of popping a bubble around it and dealing with it as if it were a much, much simpler circuit, right? So we're going to, in order to perform analysis on the R2R DAC, we're going to have to perform several Thevenin equivalencies, which is going to be fine. We're going to do it, and it's going to be awesome. So, Thevenin analysis lets us calculate the black box behavior of a section of a circuit. It is a form of circuit simplification that also lets us simplify voltage and current sources. So that's the trick, right? Normal circuit simplification doesn't work here because we have multiple things that could be acting as voltage sources. So we're going to, like using Thevenin analysis, we're going to be able to collapse as many of those as we need to into a single voltage source that hopefully will have the right output voltage, right? So, from the perspective of 2 points on a circuit, i.e. a load, the behavior of any network of voltage sources, current sources, and resistors can be modeled as one voltage source in series with one resistor. The equivalent voltage is called the Thevenin voltage. The equivalent resistance is called the Thevenin resistance. Incidentally, there's another simplification technique that's kind of parallel to this one. If you would rather to make the circuit into one that has a current source rather than a voltage source, there's another type of analysis that we're not going to get into called Norton analysis, which is essentially, it's like a symmetric technique to Thevenin. It just produces a current source instead of a voltage source if that's what you need. So, let's review the algorithm for producing a Thevenin equivalent circuit. In order to calculate a Thevenin equivalent circuit, 1. Redraw just that part of the circuit that you are trying to simplify. Calculate the Thevenin equivalent resistance. So in order to calculate the equivalent resistance, rewrite all voltage sources as short circuits and all current sources as open circuits. You should now be left with a network containing just resistors. Using parallel and series resistor laws, simplify this network down to one resistor. The resistance of that resistor is your Thevenin resistance. Now, you calculate the Thevenin equivalent voltage. Return to your circuit diagram before you removed the voltage sources, but keep the load disconnected. assume that no current passes through the disconnected load. Calculate the voltage across the disconnected load using Kirchhoff's voltage and current laws. Nodal analysis is the preferred technique here, since you are calculating the voltage at a particular node. Cue demo. I'm not sure I'm going to have time for the whole demo, but we can get a start on it. So, let's imagine that we have a circuit, right? We have a source, call it 10 volts, right? Let's have a resistor, another resistor, there we go. Let's throw in another resistor here, another current source, or this is a voltage source, sorry. Let's give this one 5 volts, and then another guy right here, right? So let's, for a moment, let's say that each one of these guys is 2 ohms. All right? Except for this one, we don't even care what the resistance on this guy is. So let's, so the first step for Thevenin analysis is you have to decide what's in the box and what's not. So in this case, let's draw our dividing line. That's supposed to be a dotted line. Let's draw it right there, right? So, in fact, we are interested in performing Thevenin analysis such that we get an equivalent circuit. Where's my cursor? There it is. Oh, come on. Why are you not? Opacity, size. Gosh. Oh, because it's outside the bounding box. That'll do it every time. So, we kind of designate 2 points here. Oh, and we'll just say this is ground, because, you know. This will be point A and point B, right? So we'll try to, we'll perform Thevenin analysis to find the equivalent circuit here. So first, let's find the Thevenin resistance. Copy this guy. Move her down here. Oh, I need more space. I'll just sneak her in right there. There we go. Oh, my gosh. Maybe I could just make it a bit smaller. There we go. Krita is a really nice program, I have to say. So, the first thing, we take any voltage sources, we create from them short circuits. Short circuit. Right? Now, should be reasonably easy to figure out what the equivalent resistance of this circuit is, right? So, like, this should go all the way back to high school, right? Do I have my calculator? I do. So we've got 2 resistors in parallel, right? So that's 1/2 plus 1/2, which is 1. So the equivalence of this, those two is 1, because 1 inverse is still 1. So then it's 1 plus 1/2 inverse. So the equivalent Thevenin resistance of this circuit will be 2/3. So so the question, what makes the one resistor that we cut out any different from the other resistors that also cross from point A to B? If they are in parallel, why is there only one of them being removed here? So in order to perform Thevenin analysis, you need like 2 points on the circuit. It just so happens, like in this example, that I'm doing this with some RL. So it doesn't have to be a resistor there, right? I'm just arbitrarily selecting that resistor as being the thing that I'm sort of viewing the rest of the circuit from. If we come back to our R2R analysis, and I see I'm just about out of time, so I guess I'm going to have to continue this example next time in class. If we consider, like, when we do our Thevenin analysis on this circuit, we're going to cut it in a number of different places, like here, 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 and also here. So you'll notice that like V out is designated by 2 points on the circuit, right? Eventually, we're going to bound the box all around here, right? So that we do a Thevenin equivalent on the entire circuit. But, you know, like, I don't know, maybe you have that connected to a, you know, an audio, like a headphone or something that's a load. Then you'd have like a resistor representing that load off to the side. Resistors don't have to just be like the little tiny resistors. It could be anything with resistance, which includes things that do useful things, like light bulbs can be resistors if they're the right type and stuff like that. Question: Where do we take as reference to decide what is in series versus what is in parallel? Do we take A and B as the reference point, like a voltage source? So where do we take as reference? So it really, like, it's kind of like, it's like a given to you in the question type parameter, right? With respect to this particular example, I kind of put the resistor I was interested in off to the one side, just to you know, so that I could easily do like the cut and paste job with it. But if you get a question that's like, perform Thevenin equivalent, like find the Thevenin equivalent resistance or whatever, it'll also specify like the point at which you make the cut, right? The cut is like something that you have to do intelligently, right? But yeah. Oh, so we are just choosing an arbitrary part of the circuit to measure Thevenin across to figure out what the output would be at that specific resistor. Yes, that is very well said. Thank you. So to reiterate, we are just choosing an arbitrary part of the circuit to measure Thevenin across to figure out what the output would be at the specific resistor. Yes. So this is kind of like a toy example, right? This circuit doesn't really mean anything aside from the fact that it's a bunch of resistors and voltage sources that have all been put into one diagram, right? It's like, it doesn't mean anything physically at this point for us, right? It's like, it's just one of these toy examples that you play with. This guy, on the other hand, this does actually represent something physical. So, like, the manner in which we chop this up for a Thevenin analysis will not be arbitrary, because, like, we are trying to, like, this thing has a lot more context than the other one does, right? It's like what the load is depends on the context of the circuit, right? Like, when you design a circuit, it's not just like these squiggle marks that are floating in space and then you kind of press them into a circuit board, you know? So we find the effective resistance with reference to the cut, and that's the Thevenin resistance. Yes. Taking voltage sources and making them into short circuits, and taking current sources and making them into open circuits. Yes. So it's not defined by geometry. It's just arbitrary depending on the needs of the question/circuit. Yes. Yes, 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 yes. Yeah, it's not defined. There's, like, okay. There's nothing within this circuit that betrayed RL as the one resistor that we need to perform Thevenin around. We are performing Thevenin so that we know, or we can know with more certainty, perhaps, what the equivalency of this the rest of the circuit is. And again, like, I can kind of see why Thevenin, like, it was kind of touched on in your class and you weren't drilled on it a lot, because for analyzing this type of circuit, like, there's not a huge amount of point in using Thevenin over using something like, you know, mesh analysis, right? Using mesh analysis, you could find anything out that you might want to about both these points and, like, the current through this resistor and, like, anything that you might be interested in, right? It's when we apply Thevenin to this circuit here that you're going to see why it's so useful, right? And it's useful specifically in this type of circumstance. But anyway, I've gone on enough. Are there any further questions? If not, I'll be logging off and going and having dinner. Yeah, it's kind of funny, like, I don't know, maybe it's just because, like, it was a very long time ago, and, like, I'm old. But I don't even remember Thevenin analysis being mentioned during my undergraduate education, and at that time, the Tron class took, like, 3 courses in digital circuitry, which were mostly overlapping in terms of content with each other. One of them got axed, and you now have the algorithms course instead. Okay, well, doesn't look like anybody has any questions, so thank you very much for your time and attention, and we'll do this on the board, I think, probably on Thursday. I should be feeling fine by Thursday. I'm actually feeling like I'll probably be in fighting shape again for Wednesday, so there we go. See you later, folks.